All right, welcome everybody. Here we go. I see everybody popping in here. Looks like a lot of folks are coming in. So those that are here, hopefully you have the cheat sheet handy, ready to rock and roll. And also, if you would like to, feel free to go ahead and follow along with me. I'm not going to try to cruise through this at lightning speed or anything like that. We'll kind of go through the cheat sheet itself. I'll do like a little introduction to the program as well, WinDbg that is, and especially for those that maybe have never seen it before. Cool. Let's go ahead and kick it off. All right. So my name is Jonathan Reiter, and I'm the author of Security 670, where we focus on spending a week in C++ to create an implant for the Windows platform. And we have a pretty awesome CTF at the end of that, where you take your implant that you made a little bit each day one, two, three, four, and five, adding more features as everything goes along, and you test it all out on the CTF environment, trying to get access to a number of systems on the range. So it's a really fun course. And this cheat sheet that I made was actually a recommendation from a student of mine because we do a lot of PE parsing in code throughout the class. And I just thought it's a great idea to go ahead and make a cheat sheet. So I was like, yeah, that's awesome. Let's go ahead and do that. So that's what I'm going to be doing today, walking through the little cheat sheet for WinDbg, or if you want to put the Italian little spin on it, it's WinDbg. It's always a lot of fun to say it like that. So we're going to be walking through that cheat sheet, doing some PE parsing, getting familiar with some of the commands inside of WinDbg, and how to go through and parse an executable image, which could be a .exe or could be like a .dll or even a .sys file for like a kernel driver or something like that. I saw somebody had raised their hand in Zoom. Hopefully, if you had a question, hopefully your question has been answered. Feel free to ask your question in Zoom and or Discord. I'll try to keep both open to try and help you all out. Okay, so on my Windows VM here, I just got the cheat sheet open, obviously, and what I like to do is go ahead and open up the debugger itself. And that's not how I like that window to be arranged. So go put it over there. Okay, cool. And if you're following along and you've never played around with WinDbg ever, let me give you just a little orientation of where we are right now inside the program. Okay, so this is the user interface. Okay, you have a number of different windows or panes, whatever you want to call them, that you can have open at any given time. You can see over here on the left-hand side, I have a few that have been hidden. And if you ever want any particular pane or window to basically be more permanent and fixed to a space, you can go ahead and click the little thumb pin and pin it to an area. If you would like, you can also drag one of these around and say, I want to do a little split like this, okay, which is fine. You can do a right split, left split, put it down at the bottom, or keep it in the center if you'd like. A lot of times, depending on what I'm going through, I'll have a completely different setup with these windows. If I'm actually debugging some stuff and I want to disassemble some things, I'll make sure that a disassembly window is open, and I'll kind of pin it as well. And I like to split these two. Right, so I have like a basic command window that's open on the far right-hand side. I have the disassembly at the top left and like memory down at the bottom left. And optionally, you can have a little scratch pad area or like a notes area that we'll use as we go through this cheat sheet here in just a little bit. But as I go through this, what I like to do is I like to put addresses up there, like pointers to a structure that I know about, and any other kind of notes to kind of help me keep track of where I am inside of a program or inside of like a DLL or whatever, which is very handy, at least for me. Okay, so there's plenty of other windows that you can take a look at. You have a menu bar at the top of it. We're at the Home tab right now. You can go to View, and this is where you can go ahead and open up any of the other windows. If you accidentally hit the X to close out a window, you can go ahead and bring it back by clicking on any one of these. Breakpoints, not going to dive into breakpoints really for this one. Time travel debugging, or TTD, is an absolutely amazing feature that we have here. And in a nutshell, what that provides you is the ability to go ahead and trace the execution of a program of interest. That way you have it for forever, as long as you have the trace file, and you can play back the exact same execution over and over and over again. And you can step forwards, you can go backwards. It's really cool. So you'll never miss an API call again if you have a trace. So TTD is actually kind of cool. It has some other windows, a model scripting source, memory window to let you kind of format how you want the memory to be displayed, command, and of course, some notes. All right, so on on the home window, on the very, very far left of the home window, you have a little file tab. The file tab will go ahead and open up its own little menu of sorts, which will go ahead and let you launch an executable. It'll have recent history if you've used anything with WinDbg before. So you can see I'm here quite a bit with various programs. And even the same program like Notepad, you see Notepad up here quite a bit. I love to play around and use Notepad as like a guinea pig in the course to inject into and stuff like that. We're going to use it as a guinea pig as well to showcase the cheat sheet. You can launch an executable with the advanced features. Okay, so this is where you can actually record the execution of it. You can attach to a process, you can open up a dump file, open up a trace file, so anything that's been previously recorded, you can do so right there for opening a trace file. And then attaching to a kernel, if you want to set up a kernel debugging session against another computer, that's also an option to you as well. Okay, so let's go ahead and just jump straight into it. Let's go to my recent one. Just gonna open up Notepad. Okay, so this is my recent history. That obviously might not be there for you. So what you would have to do is navigate to where Notepad is actually located, which is in a few locations. So C, Windows. Okay, and then once you're there, you can just type in Notepad and select it. Okay, so here we are inside of Notepad, and what's happened is we have hit a breakpoint. So we have a pause. We have a pause in execution. And it's not a breakpoint that we set manually or anything like that. It's a system breakpoint to go ahead and say, you have an opportunity right now to inspect some things about how Notepad is being initialized by the kernel. The system loader has done its thing. It's doing memory allocations, mapping the image into memory from disk and all that jazz. And so this is an opportunity where we can go ahead and inspect some other things. But the Notepad window, the actual program, hasn't been displayed yet because it hasn't been fully initialized just yet. And for our example, we don't care. We don't care about Notepad being fully initialized. We don't care to see the window of Notepad because we're not going to be using it for that purpose. What we're going to be jumping into in just a second is how in the world to make sense of the internal structures that make up an actual executable image. And again, we're going to be picking on Notepad, but the concepts that we go over today can be applicable to any one of these other images like NTDLL, kernel 32, even kernel base, any one of these images. They're all basically the same thing under the hood with their structure as far as Windows operating system is concerned. All right, so over to the cheat sheet. I'm just going to keep this up here on the far right hand side, and I'll move around just a little bit to walk through this with you. So at the first pane, if you will, I know it's a trifold kind of cheat sheet. So the first pane, just have some basic commands of some things that could be useful to you. I'll explain some of these in more detail. We'll show you some of them. But let's go ahead and move over just a little bit to the middle. All right. Inside of the middle pane, I have some structures that are very specific for PE parsing, whether it's done in WinDbg or whether you're doing it programmatically in any language of your choosing. Okay, so we got the image DOS header, and I plucked out some important fields, at least some important fields from my opinion that I've had over the years of doing basic reverse engineering of malware samples, drivers, all kinds of things, and also the years of being the dev for Windows. These are just my opinions of important fields from these various structures. Okay, so with image DOS header, that's basically the very first thing that you're going to find that you can see inside of WinDbg. Basically, that's going to be at the base address of the image, offset 0. Underneath that, we have another structure called image NT headers. Now, I put 64 there because we're going to be looking at a 64-bit image. There is a 32-bit version of that if you are dealing with a 32-bit image. And there is a 32-bit version of Notepad that you can take a look at and play around with as well. Okay, there's a number of important fields from that structure as well. And then there is a signature. That way you can validate whether or not you are at the proper offset, if you will, inside the image. Okay, some of these structures will have a signature or a magic field to say, hey, am I where I think I am inside of the binary? Okay, so that's image NT header 64. Image file header is nested within the NT headers. Windows loves to have everything represented by a structure, and we have multiple levels of nested structures within. So the optional, we have the file header and the optional header. Again, both of those are inside of the NT headers structure. The optional header, despite the name of it, is not really optional for executable images and for DLLs. It's pretty much a requirement. Some of the important fields there, we have the address of entry point, which is basically going to be pointing you to where the program begins execution. All right, kind of think of like the text section where the executable code should be located within the binary. All right, the image base, data directory, we'll talk about that in a little bit more detail as we start going through some of these commands here. Data directory, image export descriptor, image import descriptor, so on and so forth, right? Okay, so coming over here at the last pane here, and this is where we actually get to go through and start running some commands. Okay, if you would like, if you're following along on your own Windows VM or your Windows system if that's your host, you can go ahead and copy paste some of the stuff if you'd like to. Okay, one of the things that I recommend if you're brand new to PE parsing with WinDbg is to just go ahead and start dumping some of the structures as they are. And what I mean by that is this. Go back to the middle just for a second. I'll go ahead and copy this one out. And what we have to do here inside of WinDbg is use the DT command. There's another one called DX. We'll get to that here in a second. But the DT command allows us to display or dump a type. And the type is going to be the image DOS header. But this is a name of a symbol. And this symbol has to be held within a module, like a DLL, like NTDLL, kernel base, COM base, so on and so forth. And a lot of times you might not know where the module is or what the name of the module is that implements this particular symbol. So how in the world can you find a particular symbol? Well, that's where you can do a wildcard search. You can say DT splat and bang, and then the actual name of the symbol itself. And what's going to happen there when you go ahead and run it, it'll go through and access the Microsoft symbol server, which WinDbg should be set up to go ahead and access and pull down symbols from the symbol server. However, I highly recommend that you have offline symbols available because the access to the symbol server is finicky at best. Sometimes it goes down, sometimes it's down for just a little bit, and you're like, well, crap, I'm waiting forever for the symbol that it just won't download. So if you ever have offline repos for your symbols, that's a great way, a great thing to have. All right, so we did the wildcard search, and it quickly pulled down some symbols, and we have two modules apparently that implement this particular symbol of image DOS header. You can go ahead and take a look at any one of these. I'll just go ahead and grab the first result there. And you can do a copy paste. You can do a double right click, and it'll automatically go ahead and go down into the command window there. Let's go ahead and do DT. Now we know where it is, just to display that type. So we have every field that is inside of this structure. And you can see at the far left, we have the offsets as well. So you can see at offset 0 inside of the structure, we have eMagic. All right, eMagic is basically the 2 magic bytes that will go ahead and represent and be an indicator to say, hey, we are indeed at the start of an executable image where one is inside of memory. Okay, there's some other things too that really don't mean a whole lot to me anyway, as a reverser or a malware developer or whatever that's doing some basic PE parsing. Obviously, they do have meaning. They are important for basically the system loader, as who really cares about that. But the other field that's really of interest, aside from the eMagic, is LF because this will be a way to get to the next structure of interest. All right, so how do we actually, make this make sense? How do we see values for these fields inside the structure? Well, we have to give the DT command an address. There's a few ways to do that. You can give it an address where a module has been loaded, or you can give it the name of a module. A lot of times that works. All right, so where in the world can you grab the address of a module? Well, at the very beginning, WinDbg already gives you that information. It says mod load, and then you have an address, and then you have another address. Well, this first address is actually the start address, the beginning address of where these modules have been loaded. And then this is ending to say, hey, everything in between these two addresses is the contents of this image as it sits inside of memory. Okay, so you could go through, you could try to do like some math between these two to figure out the entire size of that image. How much space does it take in memory? You could do that. But let's say you're going through the motions and you didn't see this, you missed it, or whatever. How in the world could you see the start and ending address of all these modules? Well, there's a command for that, and the command is lm to basically list modules. And let me go ahead and just give this some more space here. Okay, so we have, again, start address and end address for all the module names. And now they're kind of like highlighted blue for us, which is cool. So you can go ahead and click on any one of these, and I'll go ahead and give you some more information about it. And what's nice about this is whenever you click on one of these, we'll just call them a hyperlink, it'll show you the command that was ran behind the scenes when you clicked on that. So you could go ahead and take this command and save that off, and for your own internal documentation, you could put it up in like your notes window to save for later. That way, you have access to that if you're creating your own little cheat sheet, if you will, for WinDbg parsing. Okay, so again, we have all these different modules that you go around, that you can go ahead and play around with. Kernel base is one example that I give you inside the cheat sheet. So this is what that output looks like if you just click on kernel base. Okay, so since we look at kernel base right now, we see the start address here. So what I like to do is I like to go ahead and keep that double clicked. And if you go to the command menu at the top, or the command tab, there's a button over here called debug, highlight, unhighlight. And what's really nice about that is, well, not a nice color, some nasty mustard color. But in any case, it'll go ahead and highlight this address. And anytime WinDbg sees the address, it'll go ahead and keep that highlight or that color there. Even more so, on the right-hand side, it'll show you all the times that it's seen that particular address. So we have the yellow, the mustard yellow color in the scroll bar on the right-hand side, which is cool. And then what I like to do inside my notes window is I'll take this address and I'll put it up here and I'll say, you know what, just for me, I want to remember that this address is reserved for kernel base, right? That's where it is. That's the base address for this particular module. Okay, so I'll keep that up there, and you can see it's a mustard yellow as well. Okay, so cool. Now we have the address. Let's go ahead and go up into our command history and look at the DT command for that structure, image DOS header. But now we can go ahead and give it the address of our kernel base DLL. So let that run. And we see the eMagic has been applied with its value of the 5A 4D, but remember your endianness, right? It's a little endian, so it's actually 4D 5A. For the MZ, the initials for Mark Zbikowski, one of the original DOS developers. And then skipping all this junk they don't care about right now, and down to LFNU. I remember LFNU is a way to get to the new header files for the image. ON248 kind of means nothing to me. I like to see some hex values more often than not. So one of the ways that you can do that is to use a dot formats command. All right, so dot formats, and I'll bring that down there with a double right click. And we'll see all different things, all different formats for that particular value. Internally, supposedly, I guess, WinDbg says ON is a decimal value. All right, we see that right there. All right, the hex representation of that is F8. We even see a time date stamp going back to 1969. Cool. You see the octal and, of course, the binary representation of that value. All right, so that's kind of cool. But how do we take this? How do we take this LFNO and how do we actually apply it to move forward inside the image to get to those new headers? Okay, so there are a lot of values inside these structures that are to be treated as something called an RVA, right? A relative virtual address, which think of it as like an offset, like an offset inside a structure like this, where you see a plus OX1A, that's an offset from where? An offset from the base. All right, so this would be the base address. So that's how you think of an RVA. Now, to actually make it make sense and to translate an RVA to something called an actual virtual address, like where we are in memory, you have to do just a little bit of math, right? But thankfully, we don't have to do math in public. WinDbg can go ahead and take care of that for us. So we do the question mark and say, hey, I want you to go ahead and make this calculation for me. And let's give it kernel base plus the XF8 coming from LFNU. There we go. We have our new address here. This is our virtual address. Go ahead and double right click. And another command that you could run is DC, all right, to basically do a dump Starting at that address, show us the straight up hex and the ASCII representation of some of those bytes if there is an ASCII equivalent. So every once in a while, it's nice just to see a raw dump, if you will, of some of these bytes and kind of see what you might be dealing with. All right, so we see PE. All right, what in the world is PE, and how can we take a better look at that? All right, so PE, if we move on over, you can look in the middle of the cheat sheet as we kind of move down the headers. Okay, these are kind of in order, if you will, of kind of how they're laid out inside the image. So we just looked at the image DOS header. So the next one we can take a look at is the image NT headers 64. So I'll just paste that in there. And we can make an assumption that this is a symbol inside of NTDLL. So we can run that one. And yes, indeed it is. And just for being curious, see if it's inside COM-base. Yeah, it is. Absolutely. All right. So you can play around with either one of those modules, NTDLL or COM-base. But what we need to do is come back up into here and let's take this address. Okay, so there we go. We have the signature 4550. Okay, if you double click on 4550, you'll see that up above at the raw dump, and that is the PE. All right, that is the signature to let you know you have indeed found the NT headers or the new header for the image. And you see in blue, we have file header and optional header. So if you would like, you can go ahead and click on those. And we also see the type. Okay, this is indeed another structure that's just been nested inside of another structure. What I'm going to do is I'd like to go ahead and highlight this just because we're moving through. And we'll say, this is for the NT headers. All right, so there we go, moving through the motions here. And then next, we can go ahead and look at the image file header to see what's there. Let's go ahead and click on that. Okay, and then it ran a brand new command. Excuse me, the dx command. Okay, so this is a nice little step up from DT. This one takes advantage of the debugger markup language, or DML. And what I like about the dx command is you can give it C++-like expressions. So let me break this down just a little bit here. All right, so we have an address. Okay, so a virtual address out there in some page of memory where this data is being held. But to make it make sense in the realm of a image file header data type, we have to do something called a cast, a typecast. So we'll say ntdll, okay, bang, and the image file header. But then we do a star or do a splat because we're dealing with an address. Think of it like a pointer. For those familiar with programming, you're probably familiar with pointers and address of operator and that type of stuff. So we're treating that as a pointer to the type image file header, right? Which is correct. But to get the data from that, we want to go ahead and dereference that. And all of that obviously is enclosed in parentheses. And then the TAC R1 is a way to indicate your level of recursion. So anytime you have nested structures, you can go ahead and automatically pluck those out based on the recursion level. All right, so inside the image file header, we don't have any nested structures, so it really wouldn't make sense to increase your recursion level. One thing else that could be beneficial with the dx command is adding the address of operator or the and symbol right before those parentheses. And what that does is it'll go ahead and give us the address, the base address of where this structure is located in memory. So I'm going to go ahead and highlight that address, and I'll put it up here as well. And you notice the format of the address is a little bit different. That's okay. It has to be prefixed with a 0x when you're messing around with the dx command. Okay, so please remember that. If you're dealing with the dx command, your memory addresses have to be a 0x formatted memory address. All right, so I got that, and I'm just going to go ahead and copy and paste that up there. Okay, so just to know that that is my pointer to image file header. Sweet. So inside of this, we have the machine x86-64 to indicate that the machine this binary is designed for was a 64-bit installation of Windows. The number of sections, we have 7 of them. So think sections like .text, .data, .rdata, pdata, .reloc, debug, stuff like that, all right? Then we have time date stamp, number of symbols, size of optional header. We see as hex F0. And what's nice about having the size of optional header is programmatically when you're trying to do some PE parsing, and let's say you're trying to figure out how in the world to get to the text section, or rather, what's the first section of this executable image, you can go ahead and take the size of the optional header and jump over it. You can go ahead and jump over the optional header, and where you should land with that calculation is at the very first section of that image. And a lot of times it is a text section. And then characteristics. Okay, the characteristics basically describe what type of image you're dealing with, like a DLL, executable image, so on and so forth, and a few other things. Sadly, there's no direct, at least not that I'm aware of, there's no direct interpretation or decipher, or decoding, if you will, of this flags field. It's basically a bit mask of various constants that are just bitwise ORed together. So you could go through it and open up some Windows header files. I think it's winnt.h. We'll have some of these flags defined there. Okay, so that's pretty much all that's important from the image file header. So we can go ahead and take a look at the optional header. You can go ahead and just for ease, you can click on that one, and you can see it is quite larger than the file header. And we see the dx command was used again. Kind of explain the syntax a little bit for the dx command, so nothing new there. The only thing new is we're just applying the typecast as the image optional header 64, right? Key emphasis right there, 64. Okay, we're dealing with a 64-bit image. All right, so I'm going to go ahead and copy that address because I'm going to go ahead and put it up here. All right, and I forgot I wanted to add the ampersand in front of this just to show you the address of it. Okay, and with that clicked, oh, there we go. Sweet. And let's go ahead and grab this one up there and say this is a pointer to the optional header. Okay. And as you see here in the output, the image base. The image base has a value that's been highlighted for us already. And if you don't have perfect recall, which I don't, there's no way, we see, hey, this has been seen before, but what is it, right? Image base kind of obviously gives it away. But you can go up in your notes and say, hey, all right, this is image base for this module, all right, kernel base.dll. Right, that way it makes a little bit more sense, right? Bring some context other than just a random name of image base and an address. All right, so we got the magic here, going back to the base of this structure here. So at offset 0, we have the magic, and we have the value of hex 20B, or 20 Bravo. And What this means is not that you are at the base address of this particular structure, but rather to say this is a 64-bit compiled binary. If you would see the magic value of 10 Bravo, then that would indicate that this is a 32-bit binary. A lot of times you'll see representation in other PE parsing programs as like PE32 or PE32 plus. Right? The plus just means 64-bit compiled binary. All right, go ahead and get rid of that. All right, we got some other things. Linker version, size of code, yeah. The address of entry point. Okay, I mentioned briefly before that this is basically going to be the start of where the code for this particular image is located. Now, the name of this field is lying to you. This is not really the address of entry point. This is not an address. This is actually an RVA, a relative virtual address. Again, think of those as just simply offsets from the base address of something. Okay, so if you're thinking, well, how in the world do I get this RVA to show me an actual virtual address so I can take a look at where this entry point is truly located in memory? Okay, so to do that, we can go ahead and do the question mark again. And let's say kernel base plus that value. All right, now we have the actual virtual address. And we'll just copy that to the clipboard. And I'm going to move over to the disassembly window. And we'll just paste that in there. All right, and it shows us we're at kernel base, bang, kernel base DLL initialize. Yeah, cool. All right, so that looks to be right. I'm not going to say with 100% certainty that it is, but we trust. All right, we trust the structures. We trust that the compilation did its thing, and the linker did its thing, and everything is just fine. Right? There's nothing suspicious here with these values. All right, so that's the address of entry point. You can see how we use that RVA to make a virtual address to see where code is actually supposed to start. Then we have base of code, section alignment, file alignment, blah, 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 blah. Lots of other stuff here. DLL characteristics, okay, not specific to DLLs. I don't know why Microsoft chooses some of the names that they choose for some of the stuff, but this is also applicable to executable images as well. Basically, this is another bitwise ORed field that says what compile time mitigations are applicable for this binary. And again, I don't know of an internal decipher or decoding of these. I'm used to doing all that by hand in C++ or C to go ahead and decipher some of those. All right, then we have the size of stack reserve and commit. Same thing for heap, loader flags. And then we have something called the number of RVA and sizes. And then at the very, very bottom, the last one here, offset 70, we have the data directory of type image data directory. All right, and we see 16 over here. What does that mean? Well, that's an indication to say, hey, inside of this is basically an array of 16 entries. So the data directory is simply an array that has 16 items inside of it that have different values or hold different information specific for this particular image. And we can go ahead and start to take apart some of that stuff and take a look at it. But first, let's just go ahead and display this type. Image data directory, okay, so we see inside of it we have a virtual address, and then the thing after that is the size. Okay, so that's basically the size of whatever entry we happen to look at inside of the data directory. Okay, so some of the things that could be inside of this data directory that would be important for people that analyze malware or reverse engineers in general, and also implant devs or mal devs that are doing some PE parsing, would be the image exports and image imports. Okay, let me go ahead and just take a look at some of these. And sometimes tab completion works if you have the right module, I think. Ah, there it goes. A little delayed, but hey, yeah. So inside of Combase, image export directory tab completion will work for that one. Okay. But actually, cool, didn't want that one. No, not going to tab complete there. Let's see if it works there. Nope. Oop, forgot the bang. Didn't matter. All right, let's see if we got the import here. That is not what I wanted in my clipboard. Come on, copy. Seriously. Yeah, doesn't matter anyway. Try Combase. Interesting. All right, so Combase has the import, doesn't have the export. NTDL doesn't have either one of them, and copy and paste was being royally finicky for that one for some reason. But imports here, the import descriptor, export descriptor, basically is a way to describe imports, exports. This image import descriptor, we have characteristics, we have a field called original first thunk, and another field, not to be confusing, called the first thunk. Okay, this is specific to how the import address table or import lookup table is created and initialized when the system loader is going about doing its mapping, mapping an image from disk and into memory. Okay, and then we have the name. Okay, the name is going to basically represent the module that is being imported. So think like NTDLL or kernel base, kernel 32, so on and so forth. I think you kind of get the idea there. All right. All right. So if you wanted to, you can make a little note that NTDLL like doesn't have image import descriptor, but COM base has that one. All right. Excuse me. Okay. All right, and then back up to the data directory for just a minute here. I want to show you what that command looks like to basically help you iterate over an array. So if you click on that one, we see the dx command in the background with the tac R1 for recursion. And we see here that we have the address, and we know about the typecast that we have to do, and we know about dereferencing pointers. Okay, but what's unique to this here is inside the parentheses, we've got the splat, but then right after that, we have the 16 inside of those brackets. The 16 says, hey, we're dealing with an array that has 16 entries, so let's go ahead and just dump all 16 of them, and we'll treat each one of them as image data directory. Okay, cool. If we attempt to make a modification to the recursion level, then we could go ahead and let's dump the fields inside of the image data directory to check out the virtual address and size. If we go through this, we see that the very first entry at index 0, we see a virtual address and a size. Okay, same thing goes for the next one down, next one down, next one down. How in the world do you even make sense of what any of this means? Well, that comes from reading documentation to figure out what index 0 is inside of this list, and that is actually reserved for exports. So all exported functions or exported information will be stored as basically an array here, right? So this is actually an array where each entry is yet another array. And to make sense of this is simply an RVA. Again, the name of the field here is lying to you. It's not a virtual address. It could be just an indicator to say you need to make this a virtual address by adding the RVA to the base address of the DLL or the image that you are taking a look at. Okay, so you can absolutely go ahead and do that. Okay, so let's just take a look at what that looks like. So question mark, kernel base, plus that value. I'm going to highlight that one and put it up here and say that's reserved for exports. And we'll just do a raw dump at that address. Okay. Let's go and scroll down here to the second page or the back side or whatever of the cheat sheet. See where we are here. Okay. Yep. Okay. Cool. Exports. Yeah. Cool. All right. So we already went through and we did the calculation of RVA to VA. And then we can go ahead and take a look at some of the more specific pieces of information for the exports. Now, before I go ahead and show you everything, let's just take a look at the type. All right, so we have a P image export directory where we have characteristics, time stamp, name, base, number of functions, number of names, address of functions, address of names, address of name ordinals. What in the world does all this make sense? What does all this mean? Stuff like that. Well, one of the things you can do is obviously apply an address for this to kind of say, hey, let's go ahead and have all the fields filled out for us. Okay, so we'll get there in just a second here. Excuse me. But we have the number of functions. Okay, so that's how many functions are being exported by that particular module. Then we have number of names. That's also an indicator to how many functions are being exported by name. Right? There's a big difference between the two. Sometimes you'll see the exact same values. The number of functions, number of names will match. But other times, DLLs, they might not want to export a function by name. They might not want you to know the name. Right? So that's where you can see a little bit of a mismatch between the two. Then we have address of functions, names, and ordinals. Anything you see here, you need to treat as an RVA, meaning you need to calculate the virtual address for these, right? Doing the math with the base address of something. Okay. All right, so we had that calculation there, and I sorted up here in the notes. So let's go ahead and use the dx command in its entirety. I'll go ahead and just copy this one here to save some time. We're getting close to the top of the hour. And we'll substitute the address there. Let's see if that works. Oh, that's right. I even forgot my own hint to you all. And as with the dx command, the address has to be prefixed with 0x. So try that again. There we go. And then we were able to directly specify a specific field within this structure, the address of names. Okay, let's go and play around with another one. Tab completion works here as well, or it should. Okay, trying to access .name. But if you were expecting an actual value here to see, no. All right, this is another RVA. And you also, when you double click this, WinDbg says, hey, this is also up here in the raw dump that we saw earlier. So what we can do with this? Well, we can go ahead and send it down into the command bar, and let's do some math. Kernel base plus that. We'll go ahead and take a look at that. We can do a DC just to kind of see what's here. And look at that, kernel base dot DLL. Let's try another command, DA. All right, dump ASCII or dump ANSI. I'll go ahead and keep on reading until it finds a null byte. And when it does, it's got that string termination there. And we see that is the name of the module. Okay, cool, kernel base. Now you could go forward from here and start to really dive into what functions and stuff like that are being exported from, excuse me, from kernel base. So let me go up to history just real quick. I'm going to get rid of the dot address of names and just show you everything already filled out. Time, date, stamp, blah, 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 blah. Name, you see how it's listed as an RVA. Number of functions, 7C4. I have no idea how many functions that is. Okay, so just about 2,000 functions being exported from kernel base. And these both match, number of functions and number of names. Okay, so it's a 1-for-1. NTDLL, I think, is off by 1. I think for whatever reason, ordinal number 8 is not exported by name. All right, so we saw right here that we could go through and start to take a look at some of these things specifically inside of the image data directory, looking at the exports, and then also going further to see how in the world we can see like the name of a module. And then also, if you happen to see this already, we see some other names here, and these are function names. All these function names are stored under here, address of names. Okay, so what we could do is, you saw before, inside the history where I said the address of names, I'll just run that again. We have an RVA. Okay, as we know, with the RVA, we have to do some math to go ahead and see where in the world this is actually located. Okay, so we can do a little DA there. Okay, or try to DC. Okay, so DC shows you everything. Okay, and these look like more RVAs. Okay, each and every single one of those is an RVA or an offset that we have to calculate. All right, so we'll do that calculation there. And we'll do a DA, and there we go. There we are. All right, something actually makes sense there. Access check. All right, so it's kind of cool being able to see how in the world you can start to manually move your way through an like a executable image or a DLL, and DLL specifically for exporting functions. Although executable images like .exes can actually export things as well. It's not specific to a DLL. But in any case, that kind of covers a majority of the cheat sheet here, going through the motions of starting at the very base address of a module like kernel base, and then working your way through LF and new to get to NT headers, and then applying the different offsets there to find out where, to see where in the world you are for image file headers, image optional headers, and going down the motions of the array inside the data directory with those 16 entries to find out exports. And right underneath exports will be imports. You can go through and process that as well. It's just a different structure that would be applicable to that one. And I wish I could fit more information on these cheat sheets because there's so much more that you can do. And I only had obviously a finite amount of room. So maybe I'll be creating a few more cheat sheets in the future to dive deeper into other things like imports, how to properly parse all of that stuff as well. And then as an added bonus, in the middle of the cheat sheet on that second page, went through and added some extra cool stuff, at least in my opinion, this cool stuff of taking a look at some hashes of DLLs that Windows already makes for you. So let me go ahead and just try and copy and paste and crush through this real quick to show you. Clear that. Okay, so basically just did a dump of a structure called the PEP. The @ is a pseudo register to say we'll go ahead and dump the PEP of this current process. And then with the dx command here, we can make up our own variable. And then with the arrow notation, we can go ahead and access a specific field within that structure. And then internally, all the modules inside of the image are stored in 3 separate lists. We have the load order, the memory order, and the initialization order. And all of those can be iterated over. You just kind of have to know the syntax for it. And I give you that syntax. Make everything on one line there. I'll run that one. Okay, so that's a way to go ahead and iterate a collection of list entry items. But that really doesn't give you anything that's useful. So we'll go ahead and do a little bit of a more complicated, fancy command with the dx to basically say, we want to create a grid. And what I want you to do is inside this grid, give me the name of the module and the hash value for that particular module. And you can go ahead and just click on one, and it'll show you the Unicode string. All right, it's another structure, right? So many structures. And down the bottom, we have ntdll. Okay, so that is the name of this particular entry, the very first one, and this is the internal hash value that was already calculated for you. Okay, so for those that like to do a lot of implant dev or mal dev, and you're trying to avoid strings in your binary, and you're trying to calculate hashes, some hash values are already calculated for you. There's already documentation on how to recalculate these from scratch. That way you can do a little comparison to see if these hash values match. Then you know that you are indeed looking at a module of interest, right? Something a lot of malware developers or implant developers kind of have to do. And we have to do something called PE parsing or PE walking, making our way down to all the modules that are being listed to find out where the exports are to call a function of interest that's been exported from that particular module. All right, so with that, we're at the top of the hour. So thank you all so very much for jumping in live here as I walk through this cheat sheet. If anybody has any questions post this stream, feel free to hit me up on Discord. I go by Shadows on Discord. That's my handle. And I'll be more than happy to answer your questions if you have any.